Hello and welcome once again to another video from movingelectrons.com in our Power PE series. Our topic for today, transmission line models. Let's read the question before we get into the details. We're going to be talking about charging current today, so basically dealing with capacitance of transmission lines. So let's read the question. What is the charging current per phase of a transmission line with the below attributes and the shown configuration? So the configuration is shown here. It's a three-phase line. It has three conductors, 12 feet apart. The system characteristics are given as it's a three-phase system, 230 kV is the voltage. It's a 60 hertz system. The diameter of conductor is 0.765 inches and there's just one conductor per phase. The total length of the transmission line is 25 miles. So here we have all the information that we need to find out what the charging current is. Before I go into defining charging current and then solving the problem, let's just quickly look at the formulas that we'll be using here. So that's the formula for the charging current per phase. It's voltage per phase over the capacitive reactance. Voltage per phase we know is voltage, line to line voltage over root 3. This we know is the formula for capacitive reactance, 1 over 2 pi fc, where c is the capacitance and that's given by 2 pi epsilon naught over ln gmd over gmr. These are properties of the transmission line. That's where the configuration comes into play, and we'll go into that once we start doing the solution for the problem. Let's though begin by defining what charging current is. So charging current is the current in the transmission line due to its capacitance. So it's the current in transmission line due to the capacitance of the line. Mostly we talk about the line having an inductance and a resistance, a transmission line. But what you've also got to realize is there's capacitance as well. Basically, a capacitor is any two conductors separated by an insulating medium. So that's where in a three-phase line, for example, there are three conductors. So there's capacitance between each of the lines. So there's capacitance here, as well as there's capacitance to ground, right? So there's this is what and the current that's involved due to this capacitance is what we refer to as charging current. This phenomena is obviously present in all transmission lines, but it is more prominent in medium length lines and long lines. So medium lines are any lines that are between 50 miles to 150 mile long, and long lines are anything that's greater than 150 miles. So this concept of charging current is mostly accounted for in longer lines. In the problem that we've been given, it's only 25 miles. I realize that, but this is just to get an understanding of the concept to how to use the formulas. But in the real world scenario, we only account for capacitance of lines when they are at least greater than 50 miles. The only place this is different is if these are underground lines. So this, when I'm talking about medium and long length line, these are lines that are open in air. But if they're underground lines, any lines that are even from 8 to 10 miles long, you would consider capacitance. That becomes an issue and one needs to account for charging current. So now let's look at the solution for the problem. We have to get to this formula, but we'll start going from 4, 3, 2, 1 because we need capacitance for capacitive reactance, and we need excuse me, the phase voltage for the final formula as well. So let's start right down here. Capacitance is 2 pi epsilon naught ln of GMD over GMR. GMD is the geometric mean distance and GMR is geometric mean radius for a transmission line. If you're not familiar with these concepts, I'll encourage you. I've done some videos on these before when I've discussed inductance, but I'll encourage you to review your notes on transmission line models. GMD basically for an n conductor system is the distance between each of those conductors. So 1 to 2, 1 to 3, so on till 1 to n, and then you have 2 to 1, 2 to 3, so on till n, and you have so on till n conductor. So the product of all of them um, to the root of n. So in this case, we have just three conductors. So we have D1 to 2, D1 to 3, D2 to 3. These are the distances from conductors 1 to 2, 1 to 3, and 2 to 3, and to the root of 3. GMR, in this case, there's only one conductor per phase. It's not a scenario where you have bundled conductors which have a separate set of formulas. So in this case, the GMR is just going to be equal to the radius here. So let's write that down. So GMR is going to be the radius. What have we been given? I think we've been given the diameter. So we've been given the diameter of the conductor, so that becomes 0.765 inches by 2 should give us the radius, and that value is 0.3825 inches. Similarly, if we go to calculate the GMR, that becomes, so the distances here I think are 12 feet. So 12, 12, and then we have 24. So D1 to 2 is 12 feet, D1 to 3 is 12 plus 12, 24. 2 to 3 is 12 feet again. And this is cube root. Remember, these are feet. So the answer we get is 15.112 feet, which we'll convert to inches because we have the radius here in inches, and when you take your ratio here, both the values should be in inches. This is 181.43 inches. So when we calculate our capacitance, it'll become 2 pi. We know epsilon naught is a constant, which is 8.854 times 10 to the power minus 12. And then you have divided by ln of 181.43 divided by 0.3825. And when you calculate this, you should get a capacitance of 9.03 times 10 to the power minus 12 farads per meter, or 9.03 picofarads per meter. So I'll encourage you to double check these calculations. I have checked them myself, but a lot of numbers involved here. There's always a potential for something going wrong. So that's your step 1. You need to calculate the capacitance, and that's how you'll go ahead and do that. Your step 2, now that you have your capacitance, you will find out your capacitive reactance. Or since you need the capacitive reactance to be in the denominator here, you can straight away find out 1 by xc. So 1 by xc is 2 pi fc, which is 2 times pi times 60 times 9.03 times 10 to the power minus 12. One thing to remember though is this value is per meter. Since the capacitance is distributed evenly along the transmission line, we need to consider the total length of the transmission line, which is 25 miles. So we will convert that 25 miles. If you convert that to meters, that is 40.23 kilometers, or 40.23 times 10 to the power 3 meters. So we will multiply our capacitive reactance with the total length of the line, and then the value we get here is 136.9 times 10 to the power minus 6 ohms. Now that you have this, your step number 3 is just calculating your line to neutral voltage, which is your line to line voltage by root 3. We've been given in the problem the phase voltage is 230 kV. So that's the phase to phase or line to line. So that's 230 times 10 to the power 3 because it's kV divided by root 3 should give me a value of 132 point, let's put the decimal clearer there, yeah, 132.7 times 10 to the power 3 volts. And our final step where we find out the charging current per phase is V line to neutral over XC. So then that value is 132.7 times 10 to the power 3 multiplied by, remember this is 1 by XC already, right? So you just multiply it, you do not divide it by this value. 136.9 times 10 to the power minus 6. When you multiply that, you should get an answer of 18.19 amps, and that is your final answer. Let's go up and look at the options that are given. So your answer D is correct. You notice how here I had changed the decimal values. It's very easy to make a mistake because you're carrying around picofarads and microfarads and meters and kilometers. So just be careful of your units there to get the right answer. Once again, I'll encourage all of you to just double check these calculations, and if there are any errors, please do let me know. Before I let you go and before you even get to the sample problems, I'd just like to leave you with some notes that are interesting about charging current. So I already did mention the definition and how this is mostly relevant for a medium and a long transmission line. There's some advantages to charging current. The fact that this, because of the capacitance, whereas most of the loads are inductive in nature, it generally reduces line losses by the charging current itself, and it does tend to improve power factor as well. Just because this adds leading current, the inductive loads are mostly lagging in nature, whereas if there's capacitance already in the circuit, that helps counter that. So you reduce line losses, which obviously helps with your line efficiency as well. You increase your load capacity. So these are some of the advantages that come along with it. Obviously, one of the other things is you reduce or you decrease your voltage drop, and that leads to better voltage regulation in the line. So these are some of the interesting effects of charging current. It also plays a contributing hand in the Faraday effect, if you've heard of that before. If not, I might do a video on that later, so hang on for that. So these are some of the notes I just want to leave you with to think about the charging current. I'll leave you with a sample problem. I'll encourage you to solve that and leave your answers in the comment section below. So let's say you have another three-phase line. This time it's a 500 kV line, and the frequency is once again 60 Hertz. Let's say the diameter of the conductors is 0.75 inches, and you have the length of the line this time being 100 miles, so it is a medium length line. Let's do the configuration. Let me just draw the conductors. So you have conductor 1, 2 and 3, and let's say the distance between each of them is just 10 feet this time. So you have conductors 1, 2 and 3. What else do you need to know? I think that's all the information you need to know. So for this, uh, find out the the charging current per phase. One of the other things to keep in mind that I missed in the notes here is uh, charging current is dependent only on the voltage, the frequency, and the capacitance of the line. It's independent of the load. So if you go back and look at the formula here, the charging current is dependent on the voltage, it's dependent on the capacitive reactance, and the capacitive reactance is dependent on the frequency and the capacitance. So if you can change the capacitance of your transmission line, you can change the value of the charging current, or if you change the voltage. So you should see an effect here. The voltage has been raised up. Also, the length of the line has been increased. So in effect, you're changing the capacitance because the capacitance is distributed evenly along the transmission line. So anyways, figure out the sample problem here, calculate your answers, leave them in the comment section. If there's any other feedback that you have, or if there's any questions that you have related to this topic or any other topics in the Power PA exam, I'd appreciate your feedback in the comment section below, or send me an email, nimish@movingelectrons.com. Till next time, take care and have fun.